Hello, I'm the Code Architect. Today, we're optimizing ML models with quantization and pruning. Learn how to deploy efficiently.
All right, today we're going to dive into two really powerful techniques for making your machine learning models lean, fast, and totally ready for the real world. We're talking about quantization and pruning. Let's get into it. So picture this. You've trained a state-of-the-art model. It's incredibly accurate. It's a work of art, really. But there's always a but, right? It's huge. It's slow. It eats up power like crazy. And that's the core problem we're going to tackle today. How do we bridge that gap between a brilliant model and one you can actually use? I absolutely love this metaphor. Don't think of your model as just some static code. Think of it as a high-performance engine. Optimization, that's you popping the hood, fine-tuning every little part to make it run not just powerfully, but efficiently. It's all about getting more horsepower with less fuel. Okay, our first tuning tool is called quantization. And this is all about making the numbers inside our model smaller and, well, smarter. And this has some amazing knock-on effects, as you'll see. So here's the core idea. Most models, right, they're trained using these super precise 32-bit numbers. Quantization is this clever trick where we convert those big numbers into smaller, less precise ones, like 8-bit integers. Just making that simple switch means your model gets a whole lot smaller and the calculations get way faster, all without really losing the important information. Now, you've got a couple of ways to do this. First up is post-training quantization, or PTQ. This is the fast and easy route. You just take your fully trained model and convert it. Boom, done. Great for getting something out the door quickly. But there's also quantization-aware training, or QAT. This one's a bit more involved. You actually teach the model about these lower precision numbers during the training process. It takes more work, but it really helps protect the model's accuracy. So it's that classic trade-off, right? Do you need it done fast, or do you need the absolute best performance? And the results, well, they can be pretty dramatic. Just by going from 32-bit to 8-bit, you can often shrink your model's size by a factor of 4. Just think about that for a second. That's a 75% reduction in size, and usually the hit to accuracy is tiny. That is a huge win. All right, on to our second technique, pruning. So if quantization is about making the model's parts smaller, pruning is about getting rid of the parts you don't even need. It's basically time to do a little decluttering on our neural network. It turns out a lot of neural networks are built with tons of redundant connections, these little weights that barely contribute to the final answer. Pruning is just the process of finding those unimportant connections and snipping them away. This actually connects to a really cool idea called the lottery ticket hypothesis, which basically suggests that inside every huge, dense network, there's a smaller, perfect little subnetwork just waiting to be discovered. Pruning is how we find that winning ticket. And just like quantization, there are a couple of ways to go about this. Unstructured pruning is like using a tiny, precise scalpel to remove individual connections anywhere you want. It's super flexible, but you can end up with a kind of messy, sparse model that some hardware actually struggles with. On the other hand, you have structured pruning. This is way more hardware-friendly. Instead of snipping one wire at a time, you remove entire chunks, like whole neurons. It keeps the network structure neat and tidy, which makes it much easier for processors to handle at high speed. And this just shows you the incredible power of decluttering. It's actually not uncommon for pruning to remove as much as 90% of a model's weights. Yeah, you heard me right. You can potentially get rid of 9 out of every 10 connections without a major drop in performance. It's wild. Now, this is where it's really, really powerful. See, these techniques aren't mutually exclusive. The real magic happens when you use them together. You apply both quantization and pruning to get the absolute maximum optimization. I mean, just look at this chart. On the left, that's your original model, big and kind of slow, but look what happens after we apply both techniques. The model size just plummets, and the inference speed, well, it skyrockets. This is how you transform a bulky prototype into a sleek, production-ready machine. Okay, so we've talked about the how, but let's dig into the why. Why is all of this so incredibly important for the future of AI? At the end of the day, the goal here is to break AI out of the data center. We want to run these super sophisticated models not just on giant servers, but on the devices we carry around in our pockets, devices that have limited power, limited memory, and limited battery. And this is not science fiction. It's already happening everywhere.
The AI that makes your smartphone cameras so good, the perception systems inside self-driving cars, the little health monitors in your smartwatch, critical diagnostic tools in hospitals, all of these rely on highly optimized models to work on the edge.
Let's make this really concrete. Think about a self-driving car. It needs to spot a pedestrian, another vehicle, a traffic light in milliseconds. There's absolutely no time to send that data to the cloud and wait for an answer. That decision has to happen right there, in the car, on its local hardware. And that's only possible with a pruned and quantized model that's both lightning fast and super reliable. Or what about a smartwatch analyzing your heart rhythm? It needs to run that analysis 24/7 without killing the battery in an hour. The only way that works is with a tiny, hyper-efficient model that can live right there on the device. That's the real power of optimization. But, and this is a really important but, here's a crucial word of caution. As you're shrinking and simplifying your model, you have to check your work. You must always validate that final optimized model on real-world data to make sure you didn't accidentally sacrifice too much accuracy for all that efficiency. It's a balancing act. By mastering these techniques, you're not just making models smaller, you're fundamentally changing where and how AI can be used. You are literally unlocking its potential to run anywhere, on any device, making our world smarter and more accessible for everyone. And that brings us to the final big question. Now that you know how to build AI that is not just brilliant, but also practical, efficient, and can be deployed anywhere, what are you going to build with it?
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.